Hello all of you. Welcome to the fourth lecture of the course on analysis and modeling in chemical engineering. In the last lecture, we have started doing the example of the spring and a dashpot, and we developed a fundamental model for this problem. And before that, I told you three types of modeling, which are fundamental, which are based on accepted theories, empirical, which are basically based on experimental data, fitting to the data, and the third one is the modeling by analogy. So today, what I would do in this lecture is to develop the model for the same problem of spring and dashpot, which are empirical and models by analogy. So just to recap the problem that we were doing, so we have a block of mass m that is being pulled down with a force, external force Fe, that can be a function of time, and it is supported to the wall with a spring of a stiffness constant K and a viscous dashpot of a viscosity mu. And in the beginning, it is somewhere here, and it was stationary to begin with, and then this force is being applied, and what will happen is this block will move down and eventually it will reach a new equilibrium. But before it does that, it may oscillate a bit in that position. That depends on the value of the parameters k and mu and m, and we have discussed that using this idea of this Newton's second law. We wrote the force balance for this block m, which basically consists of the force that is applied and then the spring force and the dashpot force that we have already done, and then I told you how we can numerically solve that and things like that. But let us think about a completely different approach of solving this problem. Maybe we can think about the approach that would predate Newton when he has given this second law. If we are doing it before the time Newton invented this law, how we could have come up with a model for this kind of a problem, right? So, of course, even before Newton, one can imagine of performing an experiment, and that experiment can have this block that is hanging again with a spring and a dashpot. So, this is like experimental things that one can, I believe, still make in those times. And then one can measure the displacement x of t as a function of time, and maybe as a function of the external force, the stiffness constant and viscosity and so on, right? So, one can prepare an experimental data on this particular system, maybe for different values of the masses, different value of the stiffness k, and different values of the viscosity, and we can get a set of data, and that data we can apply some kind of statistical regression or fitting of a mathematical model and come up with a model of that is purely mathematical in nature. I would say it is empirical. The reason being, there is no physics. I am just taking the experimental data, I am doing some regression, I am coming up with a model that is purely mathematical in nature. It does not come from any physical laws as such. Of course, we will show that it may turn out to be the same as what one gets by Newton's second law, but to begin with this particular model, we are not using any physical laws to begin with, right? So, one of the general models which are commonly used is the idea of a linear model, and that of course depends on the physics of the system that was there, and in this case we do not know the physics, but this is one of the common approaches that is used anyway, and in many cases this linear model works very well. What is meant by a linear model? In a linear model, we assume that, let us say, if you have an external force Fe1, let us say a constant external force Fe1 that give rise to some displacement Xe1, and let us say you have some other external force Fe2 that give rise to a displacement of Xe2. What the linear model tells me, or what linearity tells me, is if I now have a net force of Fe1 plus Fe2, the net displacement is going to be Xe1 plus Xe2, right? So, going back to the idea of model response, what I have done earlier. So, I told you I want to make a function of output and input. In this case, we are trying to create a function of this Xe as a function of Fe, right, or x as a function of Fe. It is a model. And by linearity, what I mean is that if I know that xc1 is that function of fe1 and xc2 is that function of fe2, then in that case, if I sum up fe1 and fe2, I am going to have something like xc1 plus xe2 as the same function of fe1 plus fe2. That is the idea of linearity. It doesn't always work. In that case, we will make non-linear models, but in this particular case, it will work, and in many other cases, this model does really work pretty well. So, a general mathematical form of that linear model is the following. We can think about this model as some kind of differential equation on both sides, left hand side and right hand side. On the left hand side, we have these parameters which one has to evaluate by fitting, and then xn denotes the nth derivative of x with respect to time, xn minus 1 is n minus 1th derivative with respect to time, and so on. And on the right hand side, again we have some empirical parameters that one has to evaluate by fitting, and FEM again is the mth derivative of FE with respect to time, and FEM minus 1 is the m minus 1th derivative with respect to time, and so on and so forth, right. So, in general, I am defining this y superscript bracket L as the lth derivative of any value of y with respect to time, right. So, now one can imagine that doing an experiment of this sort and doing for different parameters and trying out different linear models. In this case, we already have seen in the last class that this model that we got from the Newton's law does work pretty well. So, one can think that if I now make a totally empirical model considering only these terms, that means only the second derivative of x, first derivative of x, and x itself, and on the right hand side only the fe term, none of the derivatives, that mathematical form is going to be identical to the form that we have got from the Newton's second law. Of course, it is an empirical model, so this is not the understanding that we begin with, but since we have already shown that this fit works well, so therefore, one can expect that by doing this kind of an empirical fitting, one can in fact get something very similar. It is not necessary, one can get probably a third order differential equation that also works, but in what is most likely is we will get by this kind of a fit something similar to whatever we have got from the Newton's second law. So, then we do have an empirical model and we will fit it and we will get these parameters in this particular model, right. So, I am giving an example of a simpler model to begin with for a different problem, not the same problem, just to demonstrate the idea what we are trying to do, right. So, let us say y is some experimental value that I am getting as a function of some variable x, not the same as the displacement in the example I am doing. I am talking in general sets of experiments where we have some input variable x and output variable y, and let us say these markers represents different experimental points that I get by doing the experiment. And let us say I assume that we have a linear equation modeling this system, and in this case I assume that it is not a differential equation, let us say it is just a line. By looking at the experimental data itself, one observes that it may be following more or less a line, not exactly, but more or less a line. So, I can do this kind of a fit, and probably you have seen these kind of things. So, this dashed line is the fit that I am doing, and the quality of this fit one can find in variety of ways, but one of the standard ways is I compute the predicted value from the model at all these points here, 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 and so on, and I subtract the experimental value. So, this line that you see here, that is the error for this particular time, this line that you see here, that is the error for this particular time, and if I square those errors and sum it up and divide by n, what I get is some kind of a squared mean squared error, right. It is obvious why we are squaring it, because if I do not square it, you can imagine that you will have some positive error at certain points and negative error at certain points, and they may cancel each other. And if they cancel, it may give you an indication that the error is less, but in fact you have high positive error at some point and high negative error at the other point, right? But if I am squaring those error values, then I am basically not accounting for the sign of the error. If there is larger deviation, whether in the positive direction or the negative direction, that will basically contribute as a positive term that is coming there, and I have to take the mean with respect to the number of points I am taking, because more the number of points, I should in principle have a better and better fit. But basically what I also want to ensure is that I am somehow taking an average error by doing the experiment for a multiple number of points, right. So, this is one of the ways we can define the error. There are other ways as well, but this is one of the standard ways where we defined the mean squared error. Some people also take a square root of this and call it the root mean square error, that is also having a similar meaning, right. And then in this particular case, the example I am showing you, it looks like a line and the points are very well coming on a line. But if it was not happening, I could have imagined some other function. Let us say if this doesn't work, I may try a quadratic function. And if that doesn't work, I may try probably a differential equation and things like that. And I can keep on doing this exercise until I am able to fit the experimental data with, I would say, as less error as possible, right. So, clearly we do not expect that we will get a 0 error, because experimental data also may have some errors with that. But if the error is small, we can say that the model is providing a very good fit, right. So, that is the reason I am saying that we go back to the step 1 if my error is large. In that case, I probably need to change my model. But if the error is acceptable, and by acceptable it means different things to different people. For some people 1% error is fine, for some people 5% error is fine. More than people, it depends on the context why we are trying to do that. If I am trying to design an equipment, having a 5% error is probably okay, but if I want to have some accurate prediction of some variable, then 5% error may be larger, right. So, depending on the people and context, I can go for a more complicated model that may give you a lesser error, right. But in this particular case, I am showing that a linear model is also working pretty well, a linear equation in this particular case, right. So, there is a third way that also I could have done. Again, imagine that we do not know the Newton's laws of motion. Either we are doing this model before Newton was born, or when he did the Newton's law of motion, or somehow we skipped the mechanics classes when we were in college, right. But somehow we know that there is some electric circuit that behaves somewhat similar to the system that I am observing, right. So, whenever I have done the experiment, I may have certain observations. We had an earlier equilibrium and a new equilibrium, the system is oscillating in a certain way, things of that sort. And I can imagine that this looks something similar to another system in a very different context that is also giving me a similar behavior, right. So, the case in point here is this RLC circuit, where we have a resistance, an inductance and a capacitance in series. And for this particular circuit, for a given applied voltage E and for a charge Q, of course, the current is dq by dt, which is q dot in our representation. So, in that case, I do get the equation for this circuit as the following, right. Basically, whatever applied voltage that we have in E, that corresponds to a sum of the voltage drops across the resistance, that is the first one, second one, the inductance, that is the first one, and the capacitance, that is the last one, right. So, we have an analogy, and now I will go back, and of course, when I was doing the analogy model, I do not know the Newton's law of motion, but now let us say I want to compare this approach with the Newton's laws of motion. You see that the mathematical forms of both of these is identical, and in fact, I can make a one-to-one analogy of all the variables that we had in the problem. So, xt in the case of Newton's law, if I replace by qt, that is the charge on this RLC circuit, if FET, that is the external force in the Newton's law, if I replace with the applied voltage in the RLC circuit, if I similarly replace the mass of the block by the inductance, the viscosity of the dashpot by the resistance, and the stiffness by the inverse of the capacitance, it's like a one-to-one analogy, one-to-one mapping. In that case, basically, I can make an analogy between these two equations. Why it is good? Because mathematically both equations are same, and I have ways, or I may have algorithms, or I may have codes which can solve this RLC circuit, and I can simply use the same code to solve the Spring-Dashpot problem by simply changing m with L, or L with m, R with mu, 1 by C with k, and so on. I can make a one-to-one mapping of variables. I simply change all the variables, and I will basically use the same code which I have got for this particular problem of electrical circuit to solve the Spring-Dashpot problem. It is a highly powerful tool if one thinks about it. The only problem is that one needs to have this kind of a physical intuition that this RLC circuit looks very similar to the Spring-Dashpot problem that we have in there, right? In fact, the Spring-Dashpot system itself is a model by analogy of something known as a viscoelastic liquid or a viscoelastic fluid, right? This viscous component of that fluid is given by the viscosity mu in the model, and the elastic properties of the fluid is given by the stiffness k in the model. So, I can model the behavior of a viscoelastic fluid by modeling this Spring-Dashpot, and in fact, there is a name for this model. It is called the Kelvin-White model for a viscoelastic material, right? So, if I take this spring K as the elastic modulus of the viscoelastic fluid, and if I take the viscosity mu as the viscosity of the viscoelastic fluid, then we do have an analogy between the spring and a dashpot with the viscoelastic fluid, right? So, I hope I have been able to convince you is that the RLC circuit is analogous to a Spring-Dashpot problem, and the Spring-Dashpot problem is also analogous to a viscoelastic fluid. There are three problems in three different worlds. One is the problem from electrical engineering, this RLC circuit. One is a problem maybe from mechanics, the Spring-Dashpot, and one is a problem from, I would say, the fluid mechanics or transport phenomena, the viscoelastic fluid. And all these problems give you the same kind of differential equations, and mathematically speaking, all these are going to give me the same kind of solutions. And if therefore I have an algorithm for solving one of these problems, I can apply it on the other problem. Of course, on the last bit, on the comparison of the viscoelastic fluid with the Kelvin-White model, that's again an approximation, and there are other models as well of the viscoelastic fluid, and if we have time in the course, maybe we will discuss those kinds of models. But the point remains that there is a good analogy between the Spring-Dashpot and that of a viscoelastic material. So, the next thing that I want to convey here, based on the idea of systems and subsystems that we have discussed earlier, is that this problem also demonstrates two different paradigms that we use in process modeling. One is the idea of analysis. What we have done here for the Spring-Dashpot is we looked at the mass, the block, we looked at the spring, and we looked at the dashpot, and all of them had some characteristic, let us say m, k, mu. So, basically in the process of doing that, we have broken down the system of the spring, dashpot and block into its three subsystems, the mass, spring and dashpot. That is what I mean by the breaking down or analysis, and the three components are playing their role which we understood when I showed you what will happen if I change mass, what will happen if I change K, what will happen if I change the viscosity and things like that. The first components gives rise to the inertial effect. The second component is providing a restoring force. It resists the displacement. So, the equilibrium position is determined by the spring constant. And the last one provides the damping. If I do not have a dashpot, or if the dashpot is weaker, the viscosity is lower, we have more oscillations. As soon as we increase the viscosity, the oscillations are being damped and we have a more smooth kind of a behavior without oscillations or very few oscillations, right. So, this is all comes under analysis. If I know that the system is composed of these subsystems, and if we know what is the basic nature of these subsystems, we can, I would say, one by one analyze their influence on the system behavior, which is what I did in the last lecture. After I discussed the full solution, I have looked at different aspects one by one. But an equally important paradigm is this idea of synthesis, that yes, it is true that the mass and the spring and the dashpot constitute this problem, and their behavior do affect the system behavior, but then the way we combine it, what makes up this entire system is very, very important. The system behavior that we are seeing depends on how we have combined it, right. I could have imagined putting the mass m and the spring and the dashpot all in a series that would still have the same subsystems, but the system behavior is going to be very different. By the way, this 3 in series is also a model of viscoelastic fluid. It is called the Maxwell model, and that is also used for this, right. But the point being that the Maxwell model, when the 3 things are in series versus when the spring and dashpot are in parallel, they are going to have different behavior. A new behavior is emerging by virtue of how we are connecting these systems. What is the interconnectivity between the systems? And that basically imparts the system with the characteristics that we see on a system as a whole, right. So, whenever we analyze any system in this particular course, we will basically try to use both these paradigms, trying to break a system into its smaller subsystems and look at what those constituents or what those subsystems are doing in this case, and then to look at the system as a whole, that is a synthesis, and see what new behavior is emerging in the system by virtue of the fact that they are connected together in this particular way, right. So, I will demonstrate that by many examples in this course, but let us keep these two ideas in our mind, analysis and synthesis, and I will take more examples. So, let me now try to build some kind of a recipe for a mathematical modeling that we want to do. And when I say recipe, the natural tendency is to think about what we do in cooking. We talk about recipes in cooking, right. What I want to tell you is that mathematical modeling in some respects is no different from cooking, right. Why is that? Because cooking, as you know, it requires some ingredients, certain steps, and we have to follow a certain process, and if we do it in a proper manner, then we get good food, or it can yield in some kind of a disaster. The same thing applies also in modeling in that sense. We begin with certain equations, certain assumptions, certain parameters, and if we are doing it properly, then the model will predict the behavior of the system. But if it doesn't, then we are going to get wrong results, and it can really be a disaster. Maybe not that bad a disaster that we had in the cooking, but still, if the error is very large, then the model is no good, right. So, just like cooking, we need to follow some kind of a recipe, so that we are not making a mistake in the development of the model, and hoping that the model will work for the system that I want to apply it on, and gives you the minimum possible error or acceptable error, whatever is our requirement from the model. So, this is the recipe which I propose, and we will work on that in this course by multiple examples, right? I basically talk about a 3-step approach for every problem that you encounter in chemical engineering or in general whenever you want to model it, right? The first approach is to comprehend the problem, and if the drawing is not given, try to draw it, because a good drawing of what is happening in the system really makes a very good model. Why is that? Because you have a clear understanding of what is going on. You can refine the drawing as the process goes on and things like that to add more features. Having a drawing on the side is always better than to simply work with mathematical equations, right? The next step is, once we have that drawing, based on our understanding of the model, our knowledge of the physics, let's write the model. And finally, once we have solved that model, let us try to graph it and look at the solution, look at the behavior. Is it good enough? Does it make sense? Does it predict the behavior found in experiments, things like that, right? So there are 3 steps I basically want you to follow. One is to draw it, the second is to write it, and third is to graph it. Of course, there can be variations depending on the problem, but these 3 are pretty much, I would say, the standard steps that we follow in most of the problems that we do, right? What is draw it? What comes in there? So we have a problem definition. In some cases, for textbook problems, the problem is well defined. In some cases, one has to read between the lines and figure out what is the problem. And sometimes the problem is not very clearly stated. So we have to define the problem in words that can give rise to a model. It has to have a clear sense of input and output, and a clear sense of what kind of response do I want to obtain. The next step, as I said, is to do an analysis and figure out what is the system and what are its subsystems, right? And accordingly, we have to figure out what are the input variables and the output variables in that particular system. This I can do without even thinking about what kind of physics I am going to apply on this. Just by reading of the problem, we should be able to define the problem, we should be able to identify the systems and subsystems, and we should be able to identify the input and output variable, right? Once we have that drawing and once we have that understanding, then we can go ahead and ask ourselves, is the physics for this problem well understood? Let us say for a Spring-Dashpot problem, the first question is, do we know that we can apply Newton's laws for this problem? And if we do, it is great. And if we don't, then we have to think about alternate ways, maybe by empirical model or maybe by analogy, right? But if we know the physics really well, then we can go ahead and develop a fundamental model, and those models will of course invoke certain assumptions. As I was telling you, that in every model we have assumptions, apple falling from tree. If we ignore the drag and if we ignore the wind, then only we can write F equal to mg, maybe after ignoring multiple other things, right? So we have to make assumptions and we have to live with the fact that every model we build will have some assumptions, and therefore the key idea is not the fact that the models are highly accurate, but the key idea is the model has an optimum slopiness. So the errors are acceptable and the model is fast enough. If I am doing a solution, the solution is fast enough so that we can get the answers in time. And then accordingly, we will choose a basis, and that basis can be made up of fundamental and empirical equations. In the case of Spring-Dashpot, the fundamental equation was the Newton's second law, but then we also required empirical equations, the Hooke's law for the spring and the Newtonian liquid assumption for the dashpot, right? And once we have that, then we do have a mathematical model. I will come to the other steps in a minute, right? But let us go back on the flow sheet and ask ourselves what we will do if the physics is not well understood. So in that case, now my question is, do I have experimental data? If we can perform the experiments or if we have the data available, then probably we can take the empirical model approach, whatever I demonstrated you. In that case, we basically do a data fitting. We assume a model, some kind of a linear model. We do some kind of data fitting, and after data fitting, I will get the empirical equations which will form the basis of the rest of the steps. So, this empirical equation now becomes the mathematical model for the system, right. Let us say we do not even have that. So, we do not know the physics, we do not have the empirical data. Now, what we can do, right? So, now we can resort to the third possibility, that is modeling by analogy. Is the physics that you are observing or that you anticipate similar to something else you know about? In that case, we had RLC circuit analogous to a Spring-Dashpot. Is the physics that you are anticipating, if you do not have a data of experiments, then you can only anticipate, or is the physics that you see in the experiment, is that something similar to what you already know, right? And if yes, then we can develop a model by analogy, and now that becomes the mathematical model, right? And if we do not have that analogy, then the only possibility is to go back and do experiments, right? Because experiments, I repeat, are the ultimate truth, right? So, if we do not have anything else, we can always perform experiments, and the experiments, provided that we are doing a data fitting and coming up a model, as long as the model is fitting the experimental data, since experiments are the ultimate truth, that model is going to work well. The only limitation is that it is going to work well only within the range of the experimental designed space. Let us say I do the experiment within a certain range of parameters, let us say mass values from 1 kg to 10 kg, then my model is good only for that range, typically speaking. If I am doing 100 kg, then I am extrapolating my model. So, these issues will come whenever we are doing any kind of an experimental data followed by a fitting to come up with a model. One of the big restrictions is that my model is limited to, strictly speaking, the range of parameters for which experiments has been conducted. I can of course extrapolate, but we do not know how good it is going to be that. As long as we are interpolating with enough number of data points, we are good. So, the range in which the experiment has been conducted is extremely important, and whenever we use empirical equations, we need to keep that considerations in the mind, right. Let us say Hooke's law. Hooke's law, F equal to minus kx. I demonstrated that this is valid only when x is small enough. If x is very large, and if I keep on pulling the spring, I am going to eventually break the spring. So, Hooke's law is not valid for large deformations, right. So, any empirical model that we build is therefore going to have a restriction in terms of the range in which the experiments have been conducted that gave rise to this particular model. So, no matter what we did, whether we followed a fundamental approach, that is the first one, or empirical approach, that is the second one, or by analogy, that is the third one, now we have a mathematical model. And before even trying to solve this, the very first thing we should see is whether the model is consistent, and I will speak a great deal about it in this course. By consistency, I mean that do I have enough equations to find all the unknowns in the system. We talk about degree of freedom. The number of equations should be equal to the number of unknowns. If we do not have that, then the model is not consistent. If I am working with units, I need to ensure that we work in consistent units, let us say SI units everywhere or CGS everywhere, right. So, before even trying to solve it and wasting computer resources, we need to make these checks, because if you are doing a mistake in the units, or if you do not have enough number of equations to solve the system, or if you have too many equations than the number of variables, in all these cases there is something wrong in the model that you have built, right. So, if it does not meet the consistency check, you have to go back and rethink about how you have defined the problem and what approach you have taken when you went down, and what model you have chosen, how you define the conditions and things like that. So, before even solving, it is very, very important to ensure that whatever model you have built, if you solve it, hypothetically speaking, because you have not solved it, if you solve it, then you will get the solution. If it is not consistent, if the number of equations is not equal to number of unknowns, then no matter how hard you try, you will not get the correct solution, because that's a basic mathematical requirement in order to solve the problem. Similarly, if you have messed up the units, then it is not going to give you a correct answer. So you have to ensure that the units are consistent, right? So you have to do these kind of consistency checks. And finally, one has to do a solution. It can be analytical, it can be numerical, right? And finally, as much as possible, one should try to verify the model, right? So if one has experimental data, one can always compare that to experimental data. If we don't have experimental data, in that case, we can probably compare with a more complicated model, just to see that whether approximations we have made is reasonable enough, right? Or if I have a real plant data, or I have a data from a more detailed simulations, right? So I can do these things to verify the model assumptions, right? In all these cases, it is not possible, but as far as possible, we must try to verify the model. The reason being, I again repeat what I said in the earlier classes, that the model is never equal to the reality, and therefore we need to ensure that the model is closer to the reality, right? And how do we establish that? Is only by verification with an experimental data, which is the ultimate truth in the problem. So I finally come to the steps of the model formulation, and I will build on that in the coming lectures. The very first step is the basis, which can be, in the case of fundamental model, the accepted theories. In the case of empirical models, it is going to be whatever fitting I had done, right? And in the case of analogy models, it is going to be the physics of some other system that I am taking the analogy with, right? And then we have to make assumptions. There the idea is of optimum slopiness, and then we must do checks of consistency, at least of the degree of freedom, that refers to how many variables we have and how many equations we have, and I will talk more about that, and let us say the units. And then we can have a solution. If it is simple enough, we can do analytical solution without doing it on a computer, but then in most cases we have to go for a numerical solution by writing a code or a simulation software. And finally, there has to be a step of verification, right? So solution can be analytical for simple problem or numerical for more complicated problem, and verifications can be done either with experimental data or the data from detailed model and simulations. So with that, I want to stop here, and we discuss more in the next class. Thank you so much.